Hello and welcome to the video for Lab 6. So in this lab, you will be calibrating a couple of simple sensors. The first of these is a force-sensitive resistor, which is this component. And essentially what it is a resistor that when you press on it, its resistance decreases. So based on that fact, we're going to use this pile of pennies here, and each of which has a known weight, which you can look up on the internet. And by adding these pennies to the resistor, we will be able to calibrate the resistor and determine roughly how much force it's experiencing for a given output resistance. So that's the first part of this lab. And the second part will be calibrating a thermal resistor by measuring temperatures, but we'll get to that part in a little bit. So the components you're going to need for this lab are, at least for this first part, are the force-sensitive resistor, which is this component, and then a pair of alligator clips, which you will attach to the leads. And make sure that the alligator clips are attached to the force-sensitive resistor leads in a way that they are not touching. Otherwise, you'll get a short circuit. So here you see they are not touching. And that can be a little tricky. I did that before the video, so get that to work. And then here I'm placing it on a little stand because otherwise the alligator clips would hit the table, and that might get a little weird. So that's this setup right here. You can use whatever kind of little stand you want, but I do recommend some kind of small stand for the force-sensitive resistor. And next, you're going to need two resistors. You're going to need a 1 kilo ohm resistor, this is going to be the shunt resistor, and it will be used to measure current. And this here will be our op-amp feedback resistor. This is a 1 mega ohm resistor. Now, we're going to use it as a unity gain amplifier, so any value of resistance is okay. It doesn't have to be 1 mega ohm like this. Okay, great. And then you're going to need sufficient pennies. I've got a big stack of them here. So I think in my earlier run I used 30 pennies. I mean, you can use a greater number, a smaller number. It's up to you. And then we've got here our trusty op-amp is on the breadboard. Its notch is facing this direction, so I know you're all op-amp whizzes after Lab 4, so here we have the output, the inverting input, the non-inverting input, the power ground, or the low side of the power, and the high end of the power right here. And then I've already got some wires attached here. So to my positive power rail, I'm going to the positive power input to the op-amp. And on my negative power rail, or ground, I'm connected to the grounds of the op-amp, ground pin. And then I've got this blue jumper wire here jumping out the input voltage because we're going to put our sensor on this row here, row 16. Everything else on the breadboard is just for later. Not for this lab, but just for other projects. So we're only going to be using this area here. And then, of course, this is the Arduino. Okay, so let's put those resistors in. So the first thing I'll do is put in the feedback resistor, the 1 mega ohm resistor. And notice that I don't have any power yet on the power rails. Just for safety, I don't want to potentially damage any components. So while I'm assembling the circuit, I will not have it powered. So I am going to put the feedback resistor in between the op-amp output and its inverting input. So that in here would be between rows 6 and 7. Let's see if I can get this dang thing in. This is the most frustrating part of breadboards. It's getting the components in. Let's see. That'll work. That'll work. And so now the op-amp is good to go. So now we have also got two sides to the force sensitive resistor. So if you consult figure 1 in the lab instructions, you'll see we want the main part of the circuit. Essentially all it is it's just a DC current flowing from the high end of the force sensitive resistor going into the force sensitive resistor. There's some kind of resistance in here, a variable resistance depending on the amount of force on it. That'll come out of this low side wire, and then that will go through a 1 kilo ohm resistor and then back to ground. So it's just a DC, a simple DC current from 5 volts to ground through 2 resistors. And then the op amp is just sampling the voltage halfway between these 2 resistors. Based on that voltage, we can infer what the resistance of the force sensitive resistor is. And so that will accomplish our calibration, as explained in the instructions. So make sure you give that a read. Okay, so then here on row 16, we're going to jump the this to ground. That's going to be the 1 kilo ohm to ground connection. See if I can get that in there too. Come on. Okay, I'll use a different row. There we go. Nice and smooth. And then here, this low end of the force sensitive resistor, I will connect also to row 16. And then the high end of the force sensitive resistor, I'm going to put here on the positive rail. So, do you see the current path? It's going to go from high voltage into the force sensitive resistor, out of the force sensitive resistor, into row 16, then through the 1 kilo ohm resistor and back to ground. And the op amp is just sensing the output voltage, or this intermediate voltage between the 2 resistors. The op amp here is used to condition the signal, signal conditioning. So essentially, this makes sure that there's no current draw on the sensor output, and that way the rules governing the voltage divider, allowing us to figure out what the resistance of the force sensitive resistor is unaffected, right? Because if there was a different current, if there was a current going out through this blue wire, then your analysis would be different because the current would be branching, right? So the op amp is used to condition the signal and isolate the sensor output from the current flowing in the circuit to be sensed. So here I'm going to attach this white wire is attached to pin A0 on the Arduino. So this is going to measure the output voltage. So I'm going to attach that to this row here on the breadboard. If it will go in, there we go. And then finally, I've got the 5 volts and ground off the Arduino, which I will attach to the power rail and the ground. So now the circuit is energized, and I'm ready to run the MATLAB script, which is just going to print out, I'll just, well, consult the bottom of page 3 on the instructions. So all it does is it just prints out the reading on pin A0. For this lab, I recommend just recording by hand what the voltage output is for various inputs, because you're only going to need to take a couple of data points. So I hit run on this. So initially it says that there's 0 volts sensed and that's just because this resistance is so high that the intermediate voltage is below the resolution of the Arduino's analog to digital converter. And then I begin stacking pennies on this thing. So it still says 0, still says 0. Oh, now it says 0.031 volts. So now there's a very small voltage reading. Put another one on, we've got 0.08 volts. 0.09 volts. So let's take a look at what the Arduino is reading now that I've added 4 pennies to the resistor and put some weight onto this thing. So you see the MATLAB output. It is reading. It's fluctuating a little bit between the different output voltages that the Arduino is capable of reading, right? So the Arduino is a digital device, and it can only read 1024 different values of voltage between 0 and 5 volts. So that's why you see it jumping in these discrete levels, because it's ultimately recording them in a digital manner, and it can only see 1024 different values as encoded in some kind of binary format. So if I just continue placing pennies, I'm going to see the voltage increase. So the way I'm going to record my data, and I recommend that you do something similar, is that you simply take your notebook, whatever it may be, just make a little table of pennies versus voltage. And you can convert the number of pennies later to grams or some kind of mass by looking up the mass per penny later. And so here what I would do is I would say, okay, with 0 pennies, I had 0 volts. And then if I reduce the number of pennies to 1, that's still at 0 because it's below the threshold. But if I put 2, so now I'm seeing with 1 I had 0. With 2 pennies I had about 0.0103. Right? And this is not a precise value, right? Because this is limited by roughly 0.005 volts. This is like roughly the resolution that the Arduino can see. If you look at your output, you'll see that's the case. And then I add another penny. And so now with 3 pennies, I'm seeing about 0.07 volts. And with 4 pennies, now you're likely going to see different values, right? So you need to calibrate this for the own values that you see. It's about 0.015 volts with 5 pennies, or 4 pennies, excuse me. 5 pennies, I've got 0.02, 0.21 volts, right? And etc. So you're just going to perform this experiment. I think when I did this, I did about 30 pennies total that I managed to stack on here. So I just did that by kind of putting them in corners and then adding 1 penny at a time and recording the output. You can do as many as you'd like, however many pennies you have, so that you can get a good idea of the resistance versus force. So here I just added a whole nother stack, and then let's just put a whole nother stack on just to see what kind of output we get. So now I've got another big stack of pennies. Put them on there. Oops. I didn't screw up my circuit. Make sure they're all on there. All right, and so here with all these pennies on, I'm seeing an output voltage of about 0.26 volts, right? So, And then if I just press really hard on this output, I'm gonna have you watch the MATLAB output screen, and then I'm going to press really hard on the output. You'll see now the resistance is really dropping as I really press on there. So, but you could even using your calibration, once you've figured out roughly what the resistance versus force is, you could estimate how much force you are putting on there when you press. So that could be fun. Okay, so that is the first part of this lab. And I guess before we move on, I'll just give you a picture of data I collected the first time I did this experiment. And I made a little plot. And so this is the voltage versus this is the voltage versus penny weight that I measured. So you see it's not perfectly linear, but it's roughly linear. I put a couple error bars on here too, just to give you an idea of that uncertainty that I was mentioning, the digital uncertainty of the Arduino measurements, limited by, you know, only being able to read 1,024 different values between 0 and 5. And so you can see this was with many, many pennies. I don't know how many you're going to want to do. But the way you would calibrate this now is you would run a linear regression on this data set and determine the slope, right? So that would tell, after you convert this voltage, right? This is just the voltage out. You also need to convert it to resistance. And what you should find is that there is a roughly 1/R dependence of resistance on force. And when you look at the equations, you should be able to find that as the case, that you get this inverse relationship between resistance and force applied to the resistor. So that concludes part 1 of this lab. And I will now move on to the thermal resistor calibration. All right, so this is part 2 of Lab 6, and what I have here is some ice water right here in this lovely mug. I do recommend using a mug because it will insulate the water, keep it cold for longer. And get it all swished around in there nice and good so you can tell that it's roughly close to 0 degrees. And then also I have some recently boiled water. You can see the steam coming off it, fogging up the lens. So this is also some hot water. And for your measurement, I want you to, just before you measure, just before you put the thermistor in there, make sure it's just boiled, just recently boiled, so it's as close to, 100 degrees Celsius as possible. And our component here is the thermistor. Mr. Thermistor is a thermal resistor. Let's see if we can focus on this thing. Thermal resistor. And so you just stick this thing into things at different temperatures, and its resistance varies. That's why it's called a thermal resistor. And it has two outputs, so this is the other end of this big wire. You can peel apart these two sides and attach alligator clips to the to those leads. And otherwise, our circuit is exactly the same as before. So if you take a look at the circuit here, you'll see we have the feedback resistor, we have the op amp, output voltage. This is our 1 kilo ohm resistor. So everything's exactly the same as before. But now we're going to add the thermal resistor in place of the force-sensitive resistor. So it's exactly the same kind of circuit. We're just going to make a fancy voltage divider, basically. And put this on the positive power rail. Oop. All right. Okay, good to go. And make sure that the alligator leads are not touching. That would be short circuits. Okay, and then we're going to take the Arduino positive power rail or positive power, 5 volts, put it on the positive power rail, and the ground of the Arduino, stick that on the ground rail. So we are good to go. And then running the script, I'm now seeing some output voltage off of my thermistor. So this is what it's reading at. This is a nominally about 10K, 10 kilo ohms resistor at room temperature, roughly, is what the manufacturer says. See if I can focus on this. There we go. And I'm going to put it into one of these baths. So here, I'm going to put it into the hot water. And I see that the output, actually, let's do that again. Let this cool down a little bit. And here, look at the MATLAB output. It's reading about 0.7 volts, roughly, 0.6 volts. It's still cooling down a little bit from when I stuck it in there. But it's reading about half a volt at room temperature. And if I then stick it into the boiling water, see the voltage is varying quite a bit as it's heating up, getting... You're going to want to hold it in there for a little bit until... Okay, so now that is... that's our measurement, right? And it's now decreasing slightly because the water is cooling down. So very slowly is going to decrease as the water cools down. So what you're going to do is, if you have a thermometer, you can stick your thermometer. So here I have a cheap thermometer I got at Target. You don't have to use one, but you can just guess the temperature if you'd like. But we can move the camera. We can measure the temperature of the water. Here I'm reading, let's get it focused. And then stir it up a bit too. So it's been a bit since I boiled that, so it's at about 70 degrees C. And then I stick the thermistor in. I see a voltage reading. I'm seeing about 1.8 volts. And then I record that as a data point on my note sheet. So I'll just do that again, just for fun. So now I'm gonna table number 2 here. So I just read that was about 70 degrees C, and I got a voltage of, what did I say, 1.8? Yes, 1.8 volts. And remember, that's got our usual uncertainty of the Arduino's digital output, what it's capable of saying. Okay, so there's a high temperature measurement. Now you can feel free to take many more, or you could, with just boiled water, you know, this is probably going to be closer to 90 C, or even 100, depending on what your thermometer can measure. I just waited a long time, so it ended up being at 70 C. If you don't have a thermometer, you are going to want to do your measurement as quickly as you can after it's boiled. But please don't burn yourself. That would be that'd be sad. So now let's do the cold measurement. So we've got the ice water here. I've also been letting this sit for a while, so I'm gonna stir it up. Make sure it's nice and cold. My thermometer is reading about 6 degrees. Previously I was able to get a reading down to 3 degrees C, so if you don't have a thermometer and you just have some ice, you know, and you've got a lot of ice in there, my ice is, I'm losing ice quick, but I need to freeze some more in the freezer, so this is what I've got at the moment. But I have been able to get it down to about 3 degrees C previously. But anyway, okay, so that's about 5 degrees. So if I now stick the thermistor in there, make sure the MATLAB script is running, I'm going to see... Now this is insulated, right? So there's no problem if we just stick it in there. Make sure it's kind of in the middle. So I'm seeing a voltage of about 0.2 volts. Well, actually, I've got it against the wall, so let me move the thermistor into the middle of the ice. Okay, that's about 0.18 volts. Okay. Nice. So I'll record that. So now we've got 5 degrees C and about 0.18 volts with our usual uncertainty. I'm not writing on a... Oh, you can't see that. Hold on. So second data point, 5 degrees C, 0.18 volts plus or minus 0.05 volts. All right, so that's... So now we've got 2 points. If we assume the thermistor response was linear, this would be enough to actually do a calibration. The thing about these thermistors, they're not exactly linear. They're pretty close to linear. If you take lots of data points, if you have a thermometer, I encourage you to take many data points and do a full calibration. Let's also do room temperature. So my my thermostat says that it is about 18.8 degrees C in here. So I'll write that as a measurement. It's roughly 18.8 degrees C in my room at the moment. And when the thermistor is just sitting there, I've got to let it sit out for a second so that it returns to room temperature. Actually, I could maybe even help it along a little bit. But in that case, it seems a little low, 0.4 volts. Or maybe not. So when it's just sitting there at room temperature, I'm seeing about 0.34 volts, plus or minus 0.05 volts. Okay. So now using the voltage divider rules, which you should be able to derive using Ohm's law, describing the way the circuit works, you can now, you'll be able to plot temperature versus voltage. These points will lie roughly on a line, maybe something like that. You could do a linear regression on them. You could also take many more data points. And the first time I did this experiment, I did take many data points. And so here is a picture of all the data points I took, so you can get an idea of... so this is the voltage reading off the Arduino versus various temperatures. And so you can see it's kind of linear. It's actually kind of looks like it's asymptoting a little bit at low temperatures and maybe starting to asymptote again at high temperatures, maybe some kind of hyperbolic tangent or something, arctan. But you see it's roughly linear. So if you were to do a linear regression on this, you could now, if you read a voltage of, 1 volt, you could say, oh, hey, I know what temperature it is. It's about 30 degrees Celsius, right? So you would say that the device has been calibrated. And now, based on different sensor outputs, you could infer what the temperature is without having to do this kind of experiment. So that was the voltage, and the resistance I measured was like this. So it's also kind of like a inverse relationship between resistance and temperature, which is something roughly like 1 over T is how the resistance varies with temperature. So I took lots and lots of data points. Basically, I just let it get really hot, and then as it cooled down, I just took more and more data points using my thermometer. If you don't have a thermometer, you will only be able to get a couple of data points on here, but that's just fine. If you just want to take 3 points, that's cool. So that ends part 2 of Lab 6. So As always, let us know if you have any questions. This is a pretty straightforward lab, so the hardest part, honestly, is probably going to be setting up your circuit first, making sure there's no short circuits. And yeah, also, please do not burn yourself with the hot water. But I think you all can handle that, so. Yeah.